Hello everyone, welcome to a new video in which we are going to talk about all about IPv6 addresses. If you remember correctly, we have already discussed this topic in our audio notes number 3. It's not a necessity to check that first as we will be keeping a blind eye on that record. We will discuss everything about IPv6 from start to end in this video. So the IP version 6 serves as the replacement protocol of IP version 4. But why the IP version 4 needs to be replaced? Assuming that at least you know about IP version 4, which is a 32-bit address, and being 32-bit is quite limited in available address space, which I remember is around 4 billion addresses. But with the increasingly number of devices that uses internet, every device need a unique address. So to cope with problems, IANA Internet Assigned Number Authority come with various short-term solutions like implementing private IP addresses, classing them into various classes like ABC, and no doubt it hold the gate for long, but that gate is about to break cause every modern equipment actively tries to use the IP version 6 scheme. Supplying million and billion times more addresses than IPv4 is not the only strongest point that IPv6 offers. There's also improvement like better resource utilization on router. It's not that important to deep dive on the history of address exhaustion. But if even if you consider that, you could search the topic on Wikipedia and get every kind of history on that. But our exam concerns what the practical changes that we get using IPv6. The IPv6 isn't a entirely new thing as it keeps the certain practices same as IPv4. So every routing protocol needs only certain changes to act on IP version 6 as every router maintains a separate table for IPv6 addresses and to fetch data or store data in this new address table every protocol needs an update. Let's talk about the protocol update first. So in IP version 4 we use OSPF version 2 as the OSPF version 1 was an experimental alpha version and never implemented. The OSPF version 2 is the first version that is commercially available for use. And this version got an update as OSPF version 3 with support of IPv6. Even RIP, that is Routing Information Protocol, also got a version update. Original Routing Information Protocol only works in classful operations. That means it was of no use when we subnet the network. So during the times of IPv4, it also got an upgrade as RIP version 2. And with the coming of IP version 6, it becomes the RIP NG, in which the NG stands for next generation. ICMP, which stands for Internet Control Message Protocol, also gets a makeover as ICMP version 6. ICMP is the same protocol that is used to generate ping messages. Address Resolution Protocol got obsolete, and in place of that, we get NDP, which is Network Discovery Protocol. EIGRP, which is another routing protocol, just like OSPF. OSPF was a link state one, while EIGRP is a hybrid protocol. It also gets a makeover as version 6 Border Gateway Protocol, that is an external routing protocol, gets a makeover as MPBGP version 4. The letter 4 remains in the name as it does not donate which IP protocol it's using. The keyword MP is added to BGP4 to donate that it's the new version. We also switched from binary notation to hexadecimal as it will be pain in the neck to write 128-bit of binary. So it so it is quite clear that IPv6 addresses are quite written as MAC addresses with the alphabets in it because in hex notation we use alphabet up to F to represent a maximum value of 15. Converting between binary and hexadecimal will be explained in a separate upcoming video. So make sure to keep an eye on. Now let's talk about the address structure itself. So the IP version 6, as discussed, the IP version 6 is a 32-digit hexadecimal address separated in 8 equal parts with colons. Unlike IPv4 address, which is a 4-octet address separated with dots or full stop, writing 32 letters with colon in them, it's still a tedious job. So we use abbreviation for writing IPv6 addresses. The abbreviation rules are simple and quite straightforward. As the IPv6 addresses are separated in quadrats of 4 digits, if those quadrats are led by zeros, we can skip the leading zeros. And if the quadrant is full of zeros, for the 4 zeros, we can only write a single zero. And this second rule states that if there are multiple quadrats of zeros, we can directly use the double colon and router will automatically fill the double colon space with required number of zeros. However, double colon should be used only once in single address. An IPv6 addresses can be abbreviated in different types, but to make the abbreviation shortest, double colon must be used with the longest sequence of zeros expanding to multiple quadrats. Now, if you recall correctly, the IPv4 addresses are fragmented into two parts depending on subnet mask. The part of the address leaded by subnet once leaded by once in subnet is called the network portion, while the remaining address part is known as host portion. We have quite the same convention here, but this slight changes. The address is divided into three parts and sometimes in four parts, depending on the type of address. Let's discuss the three-part division first, which is first 48 bits of the IPv6 address is called global routing prefix. Global routing prefix is the authorized number set up by IANA or any other regional internet registries, or it can be defined by the ISP itself. This second part is of 16-bit and is called the subnet. This is where we do the process of subnetting in the IPv6 address. Now 48 and 16-bit completes the half of the IPv6 address, that is of 64-bit. And now the remaining 64-bit is exclusively given to the host. The host portion. We will discuss the four-part division of the IPv6 address shortly after defining various types of IPv6 address available. So the first kind of IPv6 address available is global unicast address. Global unicast address is by far the easiest understandable address in the IPv6 state. Actually, it is easier than the IPv4 address because we know that it is separated into three parts. The first 48 bits is the assigned number by a registered authority. 48 bits refers to the first three quadrats, and the fourth quadrant, that is of 16-bit, is the subnet ID. And just by incrementing the values in the fourth quadrant, we can subnet the global unicast address to up to 65,536 subnets without the effort of balancing the host portion, which will be the last 64 bits. As this kind of address is registered, it is completely routable on the internet, and usually these kind of address start with the digits 2 or 3 normally. Now the next form of address is unique local address, which acts like kind of private IPv4 addresses. The name has keyword local in it, which signifies that it is not routable on the internet and hence does not require any registration with any numbering authority. And this is where the division of IPv6 address in the four different parts originate. In the first part, that is of 8-bit, it is defined by IANA that it must be FC or FD, and RFC, that is request for comment or documentation addressing how to use some schemes to get standardization, refers that the FD must be used. So in local unicast address, we see the first 8 bits as FD and the remaining 40 bits will be some random number, random enough to avoid conflicts while routing. Then the 16-bit as subnet, while the finally 64-bit is totally dedicated to interface ID, which is host portion. The need behind unique local address is that it offers companies the benefit of saving some cost, which is expended for registering a new address for each device. It is also beneficial for those devices that do not need an active internet connection or the internet routing. And just like IPv4 private addresses, it also offers this security benefit with a disconnection from the outside network. Now there is a third type of IPv6 address, that is linked local address. This form of address, these form of address are not used for normal packet flows which contains data of day-to-day use application. Instead, these address are used by some overhead protocols and for routing. In simple words, these are router generated addresses used by router itself for proper functioning. It is divided into two parts only. The first part is of 64-bit, starting with digit FE8 and covering all the values with zeros. And the last 64-bit contains the interface ID, that is the host portion. But before we discuss what goes into the interface portion, it's a better idea to recall what configuration methods are available for us. First thing first, to enable the support for IP version 6 on a router, we have to pass command IPv6 unicast routing, and after that, just slightly modifying the IP4 command. For example, to configure address, we used to use IP address followed by the address with the subnet mask. Now we gonna use the IPv6 address followed by the address with subnet mask. Earlier, the subnet mask must be donated in decimal, but with the oncoming of IP version 6, the subnet mask can simply be donated using slash notation. Now, the configuration methods that are available earlier in version IPv4 are the static configuration, and second is dynamic configuration with the help of DHCP. The DHCP stands for Dynamic Host Configuration Protocol, which allots the IP addresses to every other connected device on the network. For on the device that require an IP address, we just have to pass the command IP address DHCP and it will automatically fetch the IP address from the configured pool on the router. In IP version 6, the static options are same, which means that by manually typing, we can assign a IPv6 address through an interface. But the dynamic options on IPv6 get an upgrade along with DHCP version 6, which just like earlier allots the addresses from a pool. We also get another method known as SLAAC, which stands for Stateless Automatic Address Configuration. DHCP and DHCP version 6 are not the today's talk, but we will discuss the stateless address auto configuration in detail here. Let's talk about the configuration of IP version 6 via static method first. So here we pass the command IPv6 address with the complete address and its prefix length. But to get the complete address, remember that the address is divided into three parts. The first portion is assigned number that is given by the IANA. The second portion is the subnet ID. But for this example, let's consider it's all blank zero because we don't want any subnet. But what should we put in the interface ID or the host portion? As if we put the zeros followed by 1, doesn't it become the identical to the another address of someone else's device on the internet? So to avoid the conflict, we use the MAC address as the interface ID. But don't be too furious because MAC address is only of 48 bits, but the interface ID on a IPv6 address requires you to enter 64-bit. So from where we fetch these 16 bits, we follow a method or you can say protocol to make up remaining 16 bits by ourselves. The protocol or the method is known as EUI64. EUI stands for Extended Unique Identifier and is a method to expand the MAC address scene as the MAC address also face the uniqueness problem because of presence of too many devices. The EUI64 protocols consist of several basic steps that if followed correctly, we get a 64-bit interface ID. So the first step is to divide the MAC address into two equal parts. For example, a MAC address consists of 12 digits, 12 hexadecimal digits, which is separated into 3 quarters of 4 digits. So here we are putting the first 6 digit on the left hand side and the remaining digits on the right hand side. And after that, we insert the values F, 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 E in between, and thus we get the EUI64 unique identifier. But there's still a chance of getting duplicate address. So the final step suggests that to invert the seventh bit of the newly formed EUI64 interface ID. So to invert this seventh bit, we have to do hex to binary conversion for the second digit of the newly formed EUI64 identifier. Because in hexadecimal, every digit represents a nibble. Nibble is a binary term that is given to the value which is half of an octet, meaning it contains the 4 bits. So the seventh bit lies in second digit. The third bit of this second digit after converting the hex into binary is the value that we have to invert. And right after inverting the seventh bit, we get the actual interface ID. There is a pretty good explanation why we need to invert this seventh bit. And the explanation lies in format of MAC address itself. This seventh bit of a MAC address is known as universal or local bit identifier, which identifies that whether a MAC address is a burned in address, meaning that it is provided by manufacturer, or a local address, which means that it's generated on the operating system. If you don't know, please understand that every internet device comes with a default factory made MAC address. But for certain reasons, we can change these MAC address in our network adapter settings. Reasons may include for testing, for masking our device on the internet, for research purpose, while the bad actors use the locally generated MAC address to spoof packages. In other words, to harm the network. It's a good thing that we understood how the EUI works, but we don't need to do it manually. The router can do it for us if we issue the command IPv6 address followed by the prefix that we get from an assigned authority, followed by prefix, and lastly with the keyword EUI-64. By issuing this command, the router will automatically grab the MAC address, splits it, do all the calculations and stuff, and give interface an IPv6 address. Finally, to configure IPv6 addresses dynamically, we can use the command IPv6 address DHCP. We do not need to specify the DHCP version 6, and after learning so much, the time has come to understand the working of SLLAC, which is an abbreviation of stateless address auto configuration. And to finally understand how does SLLAC work, we have to first know what does being stateless mean. The stateless means that there is no server to keep track of what addresses has been assigned and what addresses are to be assigned. When we compare it with other counterparts, for example, in static assignment, a network engineer keeps track of what addresses it gives to each device, while in case of DHCP, we create a pool from which the DHCP server assigns address to the host, as well as maintain a database about when the address assignment take place and when the address will be released. So here a router has to follow a very different process to check for conflict that may occur when some duplicate addresses are present in the network. The process is known as duplicate address detection, and we will study the duplicate address detection right after we get to know how the Slack process works. So let's begin. The Slack process starts right after an interface configure itself with link local address. We have already know a few things about how a link local address works, but for keeping everything straight in path, let's start from configuring a link local address. Configuration of link local address is totally automatic and starts right after we pass the command IPv6 enable on the host in this segment, as the whole point of having a link local address is to enable the layer 3 communication. As in the final point, the host will derive the global routing prefix from the configured router in this segment, and understanding a link local address is the most easiest task because it is separated into two parts only. The first part, that is of 64-bit, consists of FE8 and consecutive zeros up to the 64th bit, and finally the last 64-bit is made with the same process, which is EUI64. Each and everything are same, which you correctly recall is to take the interface MAC address and split into half. After that, inserting the double FE in middle, and finally by inverting the seventh bit, we get a total 64-bit EUI64 identifier. And by combining it with FE8 and consecutive 0, we get an IPv6 link local address. But host also need to check that the link local address are also unique. Until now, I believe that SLLAC is the process of configuring a IPv6 addresses on router, but let me clear all of us that it is a process of getting an unique IPv6 address on the host with the help of a pre-configured IPv6 on a router in this segment. So all kind of sending messages takes place in the host itself. And host means it may be a Windows, Mac, or a smartphone on the network segment. So to check for uniqueness of newly created link local address, the host will forward a neighbor solicitation message, that is a combination of IPv6 header and ICMP version 6 header sent on a subscribed solicited node multicast. And this is the point where I request you all to please visit the part 3 of this audio note series, because we have discussed this solicited node multicast address there in very much detail. But still, not to bother you, these solicited node multicast addresses are quite like link local address. Actually, it is a multicast group joined by every node for every kind of IPv6 addresses available. For example, right after configuring a link local address on the host automatically joins a solicited node multicast group for this specific link local addresses. To not to bother you checking day 3 video right now, a multicast address is also divided into two parts. The first part consists of rigid values, that is FF02 double colon 1, while the second part starts with double F followed by the last 6 hexadecimal values of the IPv6 address for which it is gonna join the multicast group. So in this case, the last 6 hexadecimal values of our link local address. So in the neighbor solicitation message itself, the IP version 6 header consists of the destination of just told this multicast group address, while the source is empty consists of all zeros. The ICMP version 6 header is of type 135 that denotes that it is a neighbor solicitation message and the target is link local address that is configured on the host. You might ask, what's the point of sending a packet with the address of oneself? A host does so to check if there are any other device configured with the same address. It will reply to it, and if no reply will come, then it assumes that its address is unique and make it permanent. And this is how a link local address configure. And after the confirmation, the stateless auto configuration process start. It start with an another form of message, that is router solicitation message. The router solicitation message is simply the asking all IP version 6 routers about the global unicast prefix use, and just like the host that joins the all node solicited multicast group, router also joins its all router solicited node group. So now the host will use its link local address as a source to generate a router solicitation message. That is again a combination of IPv6 header and a ICMP version 6 header. For destination, it will pick the router's multicast address, which will be double F02 double colon 2. That is contrastingly different from an all host solicited node multicast address, that is double F02 double colon 1. Now in the ICMP version 6 header, it contains a type 133 description, making it a router solicitation message, and double F02 double colon 2 are the addresses that is only joined by the router. So when the message arrives to a router, it will respond to it by generating a router advertisement. The router advertisement is the combination of an IPv6 header with a type 134 ICMP version 6 header. Within IPv6 header, the destination will be all host solicited node multicast, that is double F02 double colon 1. And for the source, the router uses its own link local address, and in the ICMP version 6 header, along with the type 134, it consists of prefix that was demanded by the host in the router solicitation message with a prefix length of 64 bit, and when this message arrives on the host will combine the received global unique prefix with his already generated EY64 interface ID and thus creates a stateless address. And for the final process of checking whether this newly generated address is actually unique or not, it performs a duplicate address detection. Another time, I have already told that for every kind of IP version 6 address, a device automatically joins its solicited node multicast group. The neighbor solicitation message is like the previous one, combination of IP version 6 header and ICMP version 6 header. And in the IP version 6 header, it contains the all host solicited node multicast group addresses as its destination, while for the source it contains its newly generated global unicast address. And within the ICMP version 6 header, it is a type 135 message explaining it that it is a neighbor solicitation message, again with the target of its global unicast address. I have already told why a host does so, because it expects if someone replies to these form of solicitation message, it means that the address has a duplicate and will cause problems. So in this case also, if there is no reply from anyone, the host assumes that the address is unique and will keep it for using. And we have just learned that how the Slack works. Please revisit this Slack section one or two more times to make sure that you fully understand this topic. Continuing to talk about Slack, there is a major problem with Slack that Slack does not provide the DNS information. DNS stands for Domain Name Server, which provides name to IP address resolution. And without the DNS, many services such as surfing the internet is not possible. This is one of the reasons why Slack is not used extensively. However, there are special flags that can be set on router advertisement to make a host understand from where to get the DNS information. As it is not in our syllabus, we are not going in much detail on this topic. Continuing with our syllabus, we have to remember a few multicast address group which I will going to post in my YouTube community section. So make sure to check that out. And in IP version 6, there is a term that is extensively used, and the term is addresses scope. So as we can witness, there are various type of addresses for every and each purpose. So there is artificial limitation laid on the some type of messages, and the artificial limitation up to where a message can travel is known as its scope. The interface local or the link local addresses that we just talked and configured has only limited point to point scope, which means that no further forwarding of packet is allowed on these kind of addresses. Then there is another form of address that is site local or organization local. These are the addresses configured by a network engineer to be able to routed within the organization and is not used on internet. While at last there is global addresses which has no boundaries and is completely routable on the wild internet. And this is how we finish the IP version 6 addresses in complete form. In the next part of the series, we will going to look at wireless LAN. So make sure to keep an eye on. Thank you very much for your time and patience.